SwayamPrabha. Digital India. Educated India.
In this lecture, we will look into some numerical examples related to composites. So, here there is one problem which is related to a composite ply, and the ply is as usual unidirectional for our case. It contains 60% by volume of carbon fibers. The properties of carbon fiber is given, and there is epoxy matrix, the properties of epoxy is given. We have to find out the longitudinal elastic modulus and tensile strength. So, the given data is we have Vf equal to 0.6, 60% as given. So, Vm, which is 1 minus Vf, is equal to 0.4. And our goal is to find out the elastic modulus E1 of the composite. So, as we know, the equation is E1 F multiplied by Vf plus Em multiplied by Vm. E1F is given to us. So, 294 multiplied by 0.6, and Em is given to us 3.6 multiplied by 0.4, and the entire thing in GPa, and finally the value comes to be 177.84 GPa. Now, we have to find out the tensile strength, which means what is the stress this ply can bear. Now, here if we keep increasing the stress, so as we looked at before, suppose there is fiber and matrix, if we keep increasing the stress, our strain remains same for both fiber and matrix, and accordingly based on their elastic modulus they are stressed. So, when we keep loading it, either the matrix or fiber will fail first, and whatever fails first, accordingly that determines the tensile strength of this material or the tensile stress of the composite during failure. Now, we know the ultimate tensile stress in the fiber and its corresponding Young modulus. So, the ultimate tensile strain is for the fiber sigma 1 Fu divided by E1 F. Now, sigma 1 Fu we know 5.6 GPa, and E1 F is 29.4 GPa, and that gives the value to be 0.01905. So, that is the amount of strain it can bear, the fiber. Similarly, the ultimate tensile strain of the matrix is sigma mu divided by Em, and sigma mu we know it is 105 megapascal, and the elastic modulus is 3.6 gigapascal. So, if we divide it, the value that we get is 0.0292. So, we can see that the the fiber material reaches its ultimate strain first. So, if we keep loading it, the fiber would fail first. Now, so during failure the strain in fiber would be 0.01905. So, in the strain in the matrix would also be 0.01905. Now, when the strain in the fiber is 0.01905, the stress is 5.6 GPa, but the stress in the matrix is not the ultimate stress, rather it is 0.1905 multiplied by the elastic modulus. So, if we want to find out the stress in matrix during failure of fiber. So, you may want to call it epsilon m, let us say we call it epsilon m star, and at that time the stress is 0.01905 multiplied by 3.6 and that is in gigapascal. And stress in fiber during failure is epsilon 1 f, if we call it epsilon 1 f star, that is equal to epsilon 1 f u, and that is equal to 5.6 GPa. So, finally, the tensile strength of the ply is, if the stress in the matrix is sigma m star. So, its contribution to the tensile strength, it is just sigma m star multiplied by 0.4, and then for the fiber part we multiply that with 0.6, and the final value that we get is 3.3874 gigapascal. Now, let us look into another problem. Here we are supposed to evaluate the transverse modulus E2 of a composite ply. If the properties given are E2F, the transverse elastic modulus of the fiber is 14.8 GPa, EM is 3.45 GPa, nu m is 0.36 and Vf is 0.65. Now, to do this, first we need to find out Em star, and Em star is Em by 1 minus nu m square. So, 3.45 GPa by 1 minus 36 square, and that gives Em star as 3.964 GPa. And then E2F we can have as it is, and Vf is given to be 0.65. So, Vm is 1 minus Vf, which is 0.35. Then we can find out our elastic modulus in the transverse direction, which we get from this relation 1 by E2 is equal to 1 by Vm by Em prime plus Vf by E2F, and then after solving this equation, E2 is found to be 7.56 GPa. Now, we need to find the same thing using the Hall-Pin-Shai relationship. To use the Hall-Pin-Shai relationship, we need a factor called eta, and eta 1 is found as E2F minus EM by E2F plus xi m plus xi m multiplied by EM. Now, let us use the xi 1 to be 1. So, if we put these numbers here, if we put xi 1 is equal to 1, finally, the value of eta comes to be 0.622. Now, if we use the Hall-Pin-Shai relationship where eta is there, then E2 comes to be EM multiplied by 1 plus xi 1 eta 1 Vf divided by 1 minus xi 1 sorry 1 minus eta 1 into Vf, and then if we put all these numbers, finally, the value comes to be 8.133 gigapascal. So, we can see that there is some difference between the experimentally obtained value and the value that we obtained from the rule of mixture based equation and the Hall-Pin-Shai equation. The next problem is, there is a glass epoxy specimen, the weight of which is 0.98 gram, and it was burned, and after burning the matrix burns out, and what remains is the fiber. The weight of the remaining fiber was found to be 0.49 gram. Now, the densities and densities of glass and epoxy are given. We have to find out the density of the composite in the absence of void, and then it says that if the density of the composite is little is given 1.5 gram per milliliter, which is obtained experimentally, then what is the void fraction? So, if the density of the experimentally obtained density is less than what we get analytically, that means there is some void which is causing the less density, and we have to find out the void fraction. Now, here we are given the weight of the fiber. So, if we divide if I divide the weight of the fiber by the density, we will get the volume of the fiber, which we can denote as small v f. So, volume of the fiber is 0.49 divided by 2.4, and that would give us, that is in milliliter, and that would give us the volume of the fiber. Now, we know the total weight of that composite, which is 0.98 gram, and we know the volume of the fiber. So, if we multiply the volume of the fiber with the density of the fiber, that gives us the weight of the fiber, that is fine, and that we already know. Now, if we take the volume of the matrix, which is unknown to us, and if we keep that as unknown, so if we take that volume and multiply it by the density of the matrix, and then we get the weight of the matrix, and the weight of the matrix and weight of the fiber gives the total weight of the composite. So, in this entire equation, our only unknown is the volume of the matrix, which we can find by solving this equation. So, total weight of the specimen is equal to 0.98 gram, and that we can find out by, we already know the weight of the fiber, which is 0.49 gram, plus if we take the volume of the matrix in milliliter, and if we multiply the volume of the matrix with the density of the matrix. So, that gives us the total weight of the specimen, which is this. So, we can solve it and find out Vm. So, Vm is 0.98 minus 0.49 and the entire thing divided by 1.2, and that will come in milliliter. So, we know the total volume of the we know the volume of the fiber, we know the volume of the matrix now. So, the total volume of the specimen, which we can call as V, and that is equal to Vf plus Vm, which is now known to me, and from here density of the composite can be found out, which we can call rho. So, it is total weight of the composite, which is 0.98 and divided by the total volume of the composite, and that will come in gram per milliliter, because our these volumes are in milliliter and this weight is in gram. So, from there we can find out the final density of the composite, and here this comes to be 1.6 gram per milliliter. Now, the question is, our theoretically obtained density is little higher than what is experimentally obtained, and the reason behind this difference is the presence of voids. So, the void volume fraction can be found as rho Ct, which means theoretically obtained density, minus rho Ce, which is the experimentally obtained density, divided by rho Ct, and then it comes to be 0.0625. So, rho Ct is our 1.6 gram per milliliter, and rho Ce, the experimentally obtained density, is 1.4 gram per milliliter. Now, this problem involves finding out the reduced stiffness matrix in both the principal material direction and 1-2 direction. We have been given the properties like E1, E2, E6, nu1, 2, and we know the ply angles 0 degree, 90 degree, 45 degree and minus 45 degree. So, we have to find out the Q matrix in the 1-2 system and in the XY system if the ply angles are this. Now, to do this, we need to first find out nu21. So, we already have nu1, 2, and we know the relation between nu21 and nu1, 2, and that is E2 multiplied by nu1, 2 divided by E1. So, if we do that, the value that comes is 0.0207. So, we can see that there is significant difference between nu21 and nu12. Now, we have to find out the constituents of the Q matrix in the material direction. So, we have Q11 and Q11 is E1 minus nu12 nu21, and that gives us the value to be 145.75 GPa. Then we have Q22, and Q22 is E2 by 1 minus nu12 nu21, and the value is 12.06 GPa, and then we have Q12 is equal to Q21, and this we can write as nu12 E2 by 1 minus nu12 nu21, or also we can write nu21 E1 by 1 minus nu12 nu21, and the value comes to be 3.016 GPa. And then we have Q66, and this is E6, and that is as given, it is 6 GPa. So, the terms like U16 Q16, Q26 are absent here, So, there is no coupling between the shear and the normal components. So, this is our Q matrix in the principal material direction. Now, we have to find out this Q matrix for different fiber orientations. So, if you talk about a 0-degree ply, so in a 0-degree ply, so a 0-degree ply would look like this. So, here the fiber is oriented in the global x direction only. So, here system 1 and so 1 2 axis and x y axis they are same here. So, there is no difference between the Q matrix with respect to x y and Q matrix with respect to 1 2. So, we can write here Q with respect to x y system for 0-degree orientation is just the Q matrix that we get for the material direction. So, it is 140.75, 3.016, 0, and then here we have 3.016, 12.060, 006, and that is in GPa. And then if the fibers are oriented suppose in 90-degree, so in this case this is our x axis as well as axis our axis 2 is in this direction. So, as well as it is same as axis 2 just in opposite sense, and here we have y axis and axis 1. So, here we can say that the properties can be found out easily from here. Now, because our fibers are oriented in y direction here, so Q11 would be just Qyy and similarly Q22 would be Qxx. So, without even having to do any transformation, we can find out the properties here. So, 12.06 now goes for a Qxx, then 3.016, 3.016 and then 145.75, then 006 in GPa. So, that is for 90-degree. Sure, like it. Now, we have to now we have to find it out for the 45-degree orientation. So, we know the for a orientation theta can be found out by applying some transformation. So, to do that the equation looks like this. So, we can put all 2's here and the expression is Q matrix T inverse multiplied by Q in the 1 2 system multiplied by T, where our T is the transformation matrix which is m square n square 2 mn n square m square minus 2 mn, and then we have minus mn mn m square minus n square, where m is equal to cosine theta and n is equal to sin theta. So, we can find it out for any theta. So, so this is the equation. So, we can do the transformation and all these elements are found out. Then finally, in the Q matrix we have Qxx, Qxy and Qxs. So, these factors of putting 2 and then getting it back, getting it removed, this was all because of we are defining two kinds of shears, one is engineering shear, one is tensorial shear, and then we can apply this formula and get out get our Q's. So, if we apply theta is equal to 45, the matrix comes to be 46.96, 34.94, 33.40, and then we have 34.94, 46.96 and again 33.40, and the matrix is symmetric. So, we get the other properties. Now, here this angle of orientation is 45 degree. So, which is just between 0 and 90. So, that is why we are getting Qxx and Qyy to be same, Qxs and Qys to be same, but for any other orientation like 30, 40, 60 we will not get this, we can get these properties different, but because it is 45 degree we are getting this to be same. If we apply the similar transformation considering it to be minus 45, then it is this our QSS changes. So, these are the values of Q matrix that we get for different types of different fiber orientations. Now, let us see if we make a laminate using these plies with different fibers of orientation, how the laminate properties look like, how the ABD matrix look like. So, let us assume that our fiber laminate orientation is this 45 minus 45 minus 45 45. So, if you want to find out the A matrix, so it would look like this first of all. So, there are 4 layers and let us assume that each layer has a thickness of 0.5 millimeter. So, this is z equal to 0, this is z equal to minus 1, this is z equal to minus 0.5. So, all are in millimeter. This is z equal to 0.5 millimeter, this is z equal to 1 millimeter. Now, if you want to find out the A matrix, we know that the A matrix is K is equal to 1 to n number of layers, and then Q matrix in the XY system for the kth layer multiplied by zk minus zk minus 1. So, what we are doing is we are just taking Q and integrating over each layer and adding it up. So, we can call this as Z0, this has Z1, Z2, Z3, Z4, and n in our case is equal to 4. So, finally, if we add this up, so in this case because thicknesses are same, it is nothing but adding up all the Q matrix and finally multiplied by the thickness of each ply. So, finally, after doing it, after putting all the numerical values, the A matrix comes to be this. That is in GPa millimeter. Now, if you want to find out the B matrix, the B matrix in this case would be 0 because it is symmetric. We can do it also and see it. Now, let us find out the D matrix, and to find out D matrix, what we do is we take k is equal to 1 to n, and Q matrix of the kth layer multiplied by z k cube minus z k minus 1 cube by 3, and then after putting all the values, what we get is this 31.307, 23.293, 16.7, 23.293, 31.307, 16.7, then we have 16.7, 16.7, 25.287, and that is in GPa millimeter cube. So, here this matrix is symmetric, and because it is symmetric, we have B matrix as 0, and apart from that this matrix is balanced also. So, you can see that number of 45 is 2 and number of minus 45 is 2, and that makes AXS and AYS 0, but this matrix is this laminate is not antisymmetric, and because it is not antisymmetric, we do not have these two components as 0. So, with this I would conclude this lecture here. Thank you.